Okay. So today's section 1.2. Functions and their properties. Some of these ideas you've heard of before, some of these you may not have, but we need to make sure we're all on the same page with it. Okay? So the very first thing we're going to talk about is what is a function and how do we write them? So function, domain, and range. What a function does is it so a function assigns every element in the domain to a unique element in the range. So what it's saying is everything that exists in its domain, it does something too and gives it a unique value in the range that's considered in the range numbers. So a function is like a linear equation. When we pick an x, we do some stuff to it and then out comes a number, right? And if it doesn't matter how many times I put that x value in, do I get the same number out every single time? So if I had an equation, let's say I had y equals x plus 4. And I picked x as 1. 1 is in my domain. And I put a 1 in. What number do I get out? 5. If I pick 1 again, what number do I get out? If I pick 1 500 times, how many times am I going to get 5 out? All 500 times, right? So that's what this is saying, is it takes everything that's in any x value you can pick. If you put it in there, you're going to get a unique answer out. Every single time. Okay? That's what that is saying. And domain, we consider these the input values. We consider this the independent variable values because we're going to use a lot of y's and x's. These are the x values. And range are the output values. It's denoted with the dependent variable. Because we use x's and y's a lot, those are our y values. Is that okay? We will ask ourselves a lot in here, what are we allowed to have for x? And so a lot of times we'll also ask, what are we not allowed to have for x? Range is harder to figure out what you're allowed to have and what you're not allowed to have algebraically, so we usually use our calculator to help us for range. But for x values, we're going to use algebra and good stuff to figure those things out. The other thing we need to talk about right now is function notation. We're used to seeing something like y equals x cubed plus 4x minus 3. We're going to step up our notation here a little bit, and we're not going to use y as much. We're going to use things like f of x or g of x. And what that just means is f is a function of x. And it tells you a lot. It tells you the independent variable is x, and it already tells me I am a function. I don't have to think about is it a function or not, because it told me in the function notation it is a function. Okay? This does not mean f times x. And so if I told you f of x equals 4x minus 2, and then all of a sudden I'm like, okay, well, what's f of 0? That does not mean f times 0. This means evaluate the function at 0. Big difference. So this is saying evaluate the function when x equals 0. So that's what that means. That's telling you to put a 0 into the equation. Tell me what I get. So if I put a 0 into this, what would we get? Yes. And so really what that told me is that told me a point. That told me a location in space. They said when x is 0, I get a -2. So just this little statement right there tells me a lot. A lot of information in that little tiny statement. Okay? And that's the beautiful thing about function notation is it saves a lot of ambiguous writing. That little f of 0 told me a lot of information. So it's really important that we understand function notation and we don't get to make it up. This is how it is, okay? Are there questions about function notation? Okay. Oh, those are all been used. So, like too many pens. There we go. Here we go. Example 1. The question is, does this define y as a function of x? So is y a function of x? So if you were to graph this, let's see what would this look like graphically? Looks like a parabola, right? Does every x value give us a unique y value?
Yep. Wait. Yeah.
This x value is only going to give me this y value, right? What about this x value? If I continued it up, is it going to give me only one y value? Is this x value going to give me a unique y value? When I say unique, it's the only one you're going to get, right? So it doesn't matter which x value I pick, I'm always going to get the same y value every single time, right? So, yes. Each domain value goes to an unique range value. You can have to use the same one, but your x value, what they're worried about is this x value right here. It's going to give you only this unique y value right here. And I know this one over here is going to give you the same y value, but that's not what they're trying to say. They're trying to say you can't have something that goes like that. Because right here, for this x value, I would get 1, 2, 3 different y values. So they're not a unique point. Is this okay? Okay. Which of the following is not a function, and how can we tell? So here's what they're trying to show you. So if you look at this, does every x value in this one go to a specific y value?
Yeah.
Yes. What about here?
Yes.
Yeah, it looks kind of crazy weird, right? But that's okay. Every x value goes to only one y value. What about here?
Nope.
This x value gets how many?
3.
3. It doesn't have a unique output. That's not okay. Yeah, it fails. It is not a function. Now, I think you guys have already learned this, but the vertical line test?
Yep.
Good. So the vertical line test tells us whether we have a function or not, right? So if we were to look at example 2 again, the first one, basically if you draw vertical lines, how many times is it allowed to cross? Once. Did it cross once there?
Yep.
Cross once there. It doesn't have to cross, but if it does cross, it only can cross One time. And that's why this guy, number C, failed. That's why I failed it. Okay, there we go. Because when you draw this right here, how many times did it cross?
3.
It failed the vertical line test. So, your vertical line test, it can only cross up to one time. Okay, so we're going to practice finding some domains. This is good. So, a lot of times when I ask you to find a domain, you have to think about the function. And this is one of the first times we're asking you to do this. So, when I'm asking you for domain, I'm asking you what x values do I get to pick? And sometimes we'll ask ourselves, well, what don't we get to pick? So think about what you know about square roots, and we're in the real number system. So what's allowed with a square root?
Positive.
Only positive numbers and 0. So when you see a square root, you have to ask yourself, what is special about this function that makes it a little bit different? What am I allowed to use under these things? So for square roots, underneath you can only have 0 or positives.
What are those? Is that like whole numbers?
No, you can have decimals in there. They just have to be positive. Yeah?
Yeah, I was just wondering, isn't it like 0 and all the positive numbers? Is that whole numbers?
Whole numbers are included. Oh, you mean natural number? Or whole, oh, yeah, but you also get rationals.
Yeah, I was just wondering.
Oh, okay. So what I'm going to ask myself then in here is I'm going to say, okay, the smallest thing I'm allowed under this square root is 0. So I need to know what makes it 0. So what makes this 0? -3, right? Now the question is, do I get bigger numbers bigger than -3 or smaller than -3? That's where we have to, and then we got to test it. So May, give me a number that's not -3. That's nice to use.
A positive number?
I don't care. Any x value you want to use. 2? Okay. So if we let x be 2, that'd be 2 plus 3. Is that allowed?
Yeah.
Yeah. So, gentlemen, so this is my 0, and we just picked 2. And that one was okay. So our set of domain is going to be -3 and bigger. So for your domain, our smallest number allowed is -3, and we get everything greater than that. This is how you write your answers in interval notation, which is why we spent all that time working on interval notation to help us now. And they tell us this is where the A sub S is the area of the equilateral triangle with side lengths S. So if there was no story problem attached to this, we would have a parabola, right? And what values are we allowed in a parabola? If it had no story problem attached to this. If I just gave you 2x squared, what can I pick for x? Anything you want, right? Because this has a story attached to it, because they told us this is the area of a triangle and these are the length of the sides, do we get to have negatives? No. So, what's the smallest we can have? 0. So, please stop. So
It's like if I move an inch, it makes a squeaking noise.
Okay, well, don't move on purpose like you were doing. Thank you. So if there's a story problem attached to it, you have to think, well, what makes sense in the story? Okay? It's like when we did the box problem and we like, okay, we had to think about how what was the biggest size square we could cut? We had to kind of go through that to figure out our window. Kind of domain and range kind of ideas. Yes. Yeah. For that one. All right. Now this one throws into complications. So we have a square root. So we need to think about, okay, we can't have anything smaller than 0 underneath it. But we also have an x in the denominator of a fraction. Right? What are we not allowed in denominators of fractions? 0. So we got two parts we got to look at this, and we got to make them work together. So let's look at the top first. So the top is the square root of x. What's the smallest x I can put in there?
0.
So the domain of this would be from 0 to...
Infinity.
That's just the top. Now the bottom, instead of saying what we're allowed, what are we not? What can x not be?
5.
X cannot be 5. Because otherwise we'd have a 0 in there, right? So what we have to do is we have to make these two work together. So the top, this one I can have everything but 5, but the top is telling me I have to start at 0. So the total domain is we're going to start at 0 and we're going to go all the way up until 5. We don't get it, we jump it, and then we start again on the other side of 5 and go to infinity. That's your domain. Right? What do you think?
Could it not be a negative?
No, because of the top. The top told us it can only be positives.
Yeah.
And then I said, okay, well, I can have all of this, but I have to kill 5. I have to get 5 out of there. So this one's telling me, you always start with the most restrictive. This is the most restrictive, the top one, right? You start with the most restrictive, and I say, okay, I start at 0, and I'm going, but I don't get 5. So to exclude 5, what I say is that I get really, 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 really close to 5 from the 0 side. And then I kind of jump over it, and then I start really, 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 really close to 5 on the other side, and then I get everything else. Is that okay? Okay. Okay. So now they want us to find the range. I will almost always find the domain first. Plus it makes us practice. So this one, there's no square root, so I don't have to worry about the square root, but I do have a fraction. So what's the only thing x cannot be? 0. So your domain is, what's the smallest I can have though? Negative infinity all the way until 0. Soft bracket, jump 0, start again on the other side and go all the way till infinity. So this, how you skip numbers in your domain with interval notation is all about soft brackets. Is that okay there? Okay. Now for range, we're going to graph it. All right. So the question is, now we're looking at y values. So what's the smallest y value I have? Negative infinity. And we got to figure out where it gets really close to, because it looks something's happening here, right? So this is one of the few times I'll actually use the trace function on my calculator. So trace. And you got to pay attention to your y values right now. So as x is going out, what's happening to y values? Getting smaller and smaller and smaller. So if I just sit here and press over, what's it getting really, really close to?
0.
Is it ever going to get 0?
Nope.
No, and then it starts again on the positive side of 0 and goes all the way up to infinity. So our range, negative infinity gets really close to 0, jumps it, starts again, goes to infinity. Now our domain and range is always going to be the same?
Nope.
No. Yeah. It doesn't. Your calculator would explode if it did. It's never going to happen. Are we okay with the domain and the range stuff? We'll do a lot. Okay? A lot. So much that you're going to dream about it. They'll be awesome. I know. You're so excited, I can tell. Yeah. Okay. All right, so the next big thing we're going to talk about is continuity. So, the very first thing for continuity we're going to talk about is a continuous graph. So that would look something like this. Most of the graphs we use in here are continuous, but some are not. Some have holes in them. And we call that a removable discontinuity. I love that movie with Shia LaBeouf, Holes, and they had to go in the desert and dig. I was thinking of that. That's a horrible thing to say. So there's different types of removable discontinuities. And your calculator will not show you a hole in the graph. Okay? How can you tell if there's a hole in the graph? If you have something here times something here, and it cancels with one of the, and these are going to cancel right here. That's where the hole would live. In this case, the hole would live at x equals -3. Whatever would make that 0, this is where the hole lives. And your calculator won't show you that. It's going to graph over it. But if you try to hit x equals -3 and you hit enter, there'll be no y value. You're in dead man land. There's nothing there. You're floating in free space, going towards a black hole. So, anyway, so the holes are where these things are going to cancel. Okay? There's two types of removable discontinuities like this. There's one where it's just the hole, and there's another one where they actually have a value for it up above, like at f of a, where it's like, so I could say here, except for when x is -3, the function is really equal to 10. And so it just makes a dot. We don't use those very much. Still a removable discontinuity. Is that okay for removable? Okay. We also have what they call a jump discontinuity. We will look at these. Usually we use these as their piecewise functions most of the time. Here's what a jump discontinuity looks like. It's like, oh, cruising along. Uh-oh, hole. But I'm going to start up here at the same spot, but I'm going to continue over here. That's a jump discontinuity. It looks like the graph kind of got broke and jumped up and then started again. Are we okay with that? And then the very last one, thank you, is an infinite discontinuity, which is like the graph that we just looked at. Yes?
In the jump ones, when it like starts up again, does it have to be like on the same line vertically, or can it?
I think it has to be. I'm sure it has to be. because otherwise we kind of have like a combo. And this next one would kind of be what that one would be, I think. Good question. The last one is an infinite discontinuity. Discontinuity. That's like an example would be the 1 over x. I always envision it like the Grand Canyon. It doesn't matter how much stuff you try to put in there, you're not going to fill it. There's a big gap. Usually we're talking about asymptotes at that point.
So would the domain be yeah.
Yep. So those are the types of discontinuities. So oh, there it is. So example 5, I'm gonna show you a picture in the book, and they want to know, are there discontinuities at x equals 2? Are they removable? So let's check out our little pictures here. So this one here, does it look like there's a discontinuity at 2?
Yeah.
Yes. What kind?
Wait.
Infinite. Right? And here's what the function looks like. So the infinite discontinuity is where the denominator equals 0. So this is an infinite discontinuity at x equals 2. What about this one? Does that look like there's a discontinuity there? No. Nope. And that's just a parabola function, so there should be something there. Now they made their picture have a hole in it. Is our picture going to have a hole in it? Actually, let's graph this one right here. Let's put that in your calculator. The x squared minus 4 over x minus 2. When you put this in your calculator, parentheses around the top and the bottom are required.
There would be, because it'd be the plus and minus.
Now, our picture doesn't show a hole, but if you hit trace and then type 2, enter, what do we get for a y value?
0 or nothing.
Absolutely nothing. Right? So what you have to look at is x squared minus 4 is the same thing as x minus 2, x plus 2, and you have an x minus 2 on the bottom. And so what happens when x is 2? What happens to these two right here? They'd cancel out. So that's why at x equals 2, there is a hole. Is it removable or infinite? Removable. If it's a hole, it's a removable discontinuity. Are we okay with that example? And you understand that your calculator won't show you the hole. You got to kind of figure it out. Okay.
It's what's left in the equation.
Well, if it's what canceled out is where the hole is.
Yeah.
Is that okay? It also explains why the rest of it looks like a line, right? Because you're left with x plus 2. So it makes sense, maybe, kind of. Yeah, No, I'm talking to myself up here. Maybe. Yeah, I'm talking to the computer. My little microphone. Thank you, Ned. Increasing and decreasing. This is also going to involve interval notation. In our interval notation, we use x values. You'll understand what I mean here in a second. So an increasing function would look something like this. Where it's always the y value, where you're looking at what is the function from left to right, are the y values going up as x's are getting bigger? And in this case, yes, it's always going up. Pay attention. Not a good time to not be listening at all. This would be a function that is always decreasing. As x goes from left to right, our y values are always getting smaller. So that would be a decreasing function. We do have constant functions. A straight line. Yeah, that'd be like y equals 2.5. That would be a constant function. It's not increasing. It's not decreasing. It's staying the same the whole time. And then we can have some that do all of it. Usually we're talking about a piecewise. Every once in a while we can make it look like an actual function. So if I gave you a picture that looked like this. It's decreasing, constant, and increasing. Here's how you would write this out. Now we always go left to right. So as x is getting bigger, what's our function doing? Decreasing until we get to -2. So you would say decreasing from -infinity all the way to -2. The function was decreasing from there to there. And then what happened at -2?
It was constant.
And so we're constant from -2 to 2. Now, they're both hard brackets because we don't know who should get the -2. Should it go with the decreasing people or the constant people? We don't know, so we're going to give it to both. And then what happens at 2? So then we're increasing from 2 to infinity. So that's how you would write that out. All right? Okay. With these kind, you're always gonna give it hard to both because we don't know. Example 6. For each function, tell the intervals on which it's increasing and the intervals on which it's decreasing. So let's graph it. So go ahead and graph this baby in your calculator. So it should have looked like this, right? So what you need to find when they ask for increasing and decreasing is you need to find maximums and minimums. So I need you to find this minimum value. So the point there is -2, 0, right? We're really worried about x values. So what does the function do? Well, remember, we read left to right. So as we come from the left, what's the function doing?
It's going down.
So, yep, so we're going to say decreasing from -infinity all the way to when x is -2. And then what happens? So increasing
-2 to infinity.
to infinity.
And beyond.
Are we okay there? Okay. So our new function g of x is this. And if you think those x squareds cancel, no, 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 they do not. Because it's a -1 over there. And when there's pluses and minuses, you can't just cancel those out because you want to willy-nilly. No, no, no. No canceling. Got it? Okay. Was I stern enough? No, I wasn't. Maybe. Let's think. Oh, I probably shouldn't make it overcomplicated. Never mind. I'll be nice right now. Okay. Let's graph it. Does anybody know where we're gonna have some problems and discontinuities?
I'm going with
1 and
negative.
-1. That's where the bottom would be 0, right?
Yeah.
So I expect some funkiness going on at 1 and -1. All right? Something's going to happen. So x squared divided by x squared minus 1. Woo! Whoa!
Whoa.
There's some crazy funkiness going on in there, yeah? Okay. Now, do we have a maximum or a minimum?
No.
Really?
Yes.
Ah, we have a maximum right there, right? So we need to find that point. So I need you to find that high point right there. So second, calculate maximum. Oh yeah, it's gonna be crazy awesome. So the minimum or the maximum happens at 0, 0. Is that okay? So you don't need to make this sketch. I'm doing this just to remind you guys what it looks like. Now, some of you with different calculators, they might give you like a vertical line right here. You need to understand when your calculator does that, it's an asymptote. You don't get that, okay? You just got to know that that's what your calculator does. So here we go, starting from the left to right. So what's the function doing at first? It's increasing all the way until where's that going to be? -1 is what makes the bottom 0 right there, right? So we're increasing from -infinity to -1. And then what happens on the other side of -1? What's it doing? It's still increasing all the way until when x is. So we have to skip -1 and we get to increase all the way until 0. Does that make sense? So then what happens at 0? Decreases all the way until what's this? That's at 1. So we're going to decrease, bless you, from 0 all the way to 1. And then what happens on the other side of 1? It's decreasing again. This is a hard bracket right here. You can't use the 1. The 1 is the vertical asymptote. It's what makes the bottom 0. So you don't get it because it's not allowed. Is that okay? And you always have a soft bracket on infinity. Good questions. We're totally not going to finish this today. But I am going to talk about boundedness. Boundedness isn't that bad.
Is it possible for the vertical asymptote to be sloped at all? It's on a graph, it's sloped it. It's not a straight up and down line. It's slightly bent inward.
It's a pixel issue on your calculator.
So it is supposed to be straight. It's just
It's a pixel thing. So if it looks like a vertical, no, I'm in the middle of a lesson. Your calculator will do that. It's the older 83s, and I'm telling you right now, if it looks kind of weird, I know it might be off a little bit, like kind of like that.
yeah.
You just need to know that that's an asymptote.
It is vertical.
Yeah. Okay. Boundedness. Hey guys, I know the lesson's getting long, but this is gonna happen in here. There are going to be times when I talk for an entire hour at you. Well, hopefully you'll participate back. But you got to keep it together. I'm not going to stop. Boundedness. What we're doing is we're figuring out all these ways to define and talk about functions that describe it without words. This one, so for boundedness, what you need to see is there an absolute maximum or is there an absolute minimum in this case? So now we're really kind of focusing on the y parts. So look at your y-axis. Is there a minimum that this is going to get to? No, this is going to go all the way down forever, right? What about up here? It's going to go up forever. So we say this is unbounded. So now here, is there a low spot we will hit that will never go lower than that?
Yeah.
Right here, right?
Yeah.
But what about going up?
No.
So we said this is bounded below. So now here, there's not an absolute low spot, but there's an absolute.
High.
So we would say that this is bounded
Above.
above. And there's one more. I'm going to wedge it in right here. So if you have, and we'll actually talk about sine waves, cosine waves and all those. These go forever, but it's going to keep oscillating. Is there an absolute high spot?
Yeah.
And an absolute low spot?
Yeah.
So we say that that is bounded. So, tomorrow we will finish these up. If you are worried about having time for homework, you can start it today because you can work all the way up through the bounded questions. And yes, they go in the